Swayam Prabha. Digital India. Educated India.
So good day to all of you, and let's continue with our discussion on subsurface monitoring around landfills. We'll quickly recap what we did last time and let's carry on and cover a little more about how we do this monitoring. So if you recall, last time we talked about monitoring above the landfill, below the landfill, and on the ground surface and on the surface of the landfill. We are basically focusing on how to monitor the environment beneath the landfill, that is to detect early and to ensure that no contamination crosses the boundary of the landfill. In plan also, we would be doing monitoring around the perimeter of the landfill and at various points above the landfill, on the landfill surface and beneath the landfill. We distinguished last time about the difference between monitoring and detection. We said monitoring, we know the source and we are keeping a regular watch, and our main objective is that the contaminants in the emissions should be within the prescribed limits. There should be no leakages, but if leakages occur, we should be able to detect it early. If we have an old facility, we have to first find the extent of contamination and then monitor at the boundaries of the contamination. Finding the extent of contamination is like detection. So detection is, we normally do not know the source. We do get contamination reported from one location. Then we have to investigate the area around that location and see how far the contamination has spread. We have to identify the boundaries of that contamination and then work backwards to detect the source as to where is that contamination coming from. So in this lecture and in the earlier lecture, we have only been looking at monitoring of subsurface environment. When we looked at the subsurface environment, we talked about the vadose zone, which is a three-phase media, and the saturated zone. And we said that the saturated zone is simpler because we just got to take out the groundwater and we want to assess the contaminants in the groundwater. It is so much more easier to take out the liquid than to take out the three phases. So we looked at various samplers like suction samplers and lysimeters last time. We looked at the free drainage sampler last time. We began discussion on the saturated zone. We looked at groundwater wells, and today we will be covering multi-port wells. And I also introduced the concept of hole sampling, which we will see a little more today using boreholes and cone penetrometers. So let's focus on saturated zone monitoring. And we said last time that monitoring is done using wells. Typically, if groundwater is flowing in a particular direction, let us say from here it is flowing from this side to this side, we'll have one well on the upstream side, so that if the groundwater is coming towards the site, we know what is the quality of the groundwater. We can have one well on the downstream side, but it is possible that a plume may go in some other direction. So normally 3 wells are kept in plan. So a total of 4 wells are used. Now one well is normally good for detecting at one level. And if you want to detect at 2-3 levels, then we can adopt a cluster of wells. So first we did this last time, why can't the same well be used for the purpose of monitoring at different levels? And we will revisit this, but at the moment we recognize that wherever there is the screen, that's where the water can be collected from, and you can use a cluster of wells if you want to do monitoring at different levels. So 1 upstream, 3 downstream. Single wells allow single level of monitoring at the level of well screens. Well clusters allow multi-level monitoring. Preferably for groundwater quality monitoring, we should not have the cast iron casings but PVC casings. We should avoid materials which can cause contamination of the groundwater because of the drilling process itself. So, drill fluid, seal materials, grouts, they can all cause problems. And if we have inserted a lot of drill fluid, we have to remember that we have to do well development, that is, suck out all these for several days or weeks before we can come back to the original groundwater which exists. So, well development means remove the drill fluid, the mud cake by pumping out the groundwater. To pick up the groundwater samples, we would like to use PVC balers or PVC pneumatic samplers. And in any case, whenever we want to go and sample at a particular location, suppose I want to pick up a sample today, then I want to come up after a month and pick up a sample, I don't just send my sampler to this level. I have to first remove the 3 times the volume of the water which is inside this casing. Why? It's a well, something may have fallen on, some foreign material may have fallen from the top. Even if it is sealed, some other algae or bacteria may start to grow. So therefore, you would like to purge. Purge means remove 3 to 5 casing volumes and then take a sample from this location. So again, just to understand, if this my landfill is here and that's my groundwater, if I was to ask you, please give me the concentration of groundwater at different locations. I wanted you to tell me what are the concentration of chlorides at these 5 points. Now it seems simple that I should make a well and monitor it, but just see what happens. When you make the well, first you make the borehole, right? And during the making the borehole, you are using drilling fluids. How will you make a borehole for a tube well? What kind of boring do you use? Do you normally use auger boring? Do you use percussion, wash? Wash boring means what? Suppose I am making a 6-inch or an 8-inch diameter well. What is the drill tool that I will use? I normally use a casing with bentonite slurry being pumped into it, and I keep on rotating the casing, and the bentonite slurry comes from outside. An exaggerated view of the casing and a drill bit at the bottom. Your fluids are coming in, this casing is rotating, and the cuttings are coming out. It keeps on cutting, you don't take out the casing, suppose you have to go very deep. The slurry which is coming from the annular space between the casing and the borehole, that carries out the material which has been cut. Once you have reached a particular level, then you put in your pipe with the screens and remove your casing. And in the annular space, you fill up the gravel. So what are you seeing here? You are seeing in this diagram, though this is a straight line, this is the borehole which has been made by the drilling equipment. But the drilling equipment is gone. You have put in a casing. The casing has holes or screen. And between the annular space of the borehole and the casing, you are putting the gravel pack. So do remember that when you remove your casing, the whole hole is full of bentonite slurry, and that bentonite slurry has nothing to do with the groundwater which exists there. And this bentonite slurry has also gone into the soil. So that's why the importance of well development and removing this. So you put the gravel, and then you put bentonite or cement grout to seal this so that nothing from the top can come here, and this screen level is where the groundwater is coming in. So when I give you this problem, that please tell me the groundwater, chloride concentrations in the groundwater at these 5 levels, you are very tempted to put a borehole, and you are very tempted to put a Suppose you put the screen, you say, I will put the screen over this entire length and then I will take the samples from this borehole. Please understand the gravel outside is making all these waters mix together. You know, this has become a high drainage media. So, anything you do to take out the water from here, the level will go down. I have to do purge 3 to 5 casing volumes, more water will come in. That water will be mixed water of all this, because the water will flow like that. So, I am not able to pick up the water from 5 specific points which represents the original condition. To do that, either I can use a well cluster of 5 wells. So, then I will put one well up to this point and just have the screen here. So that the water which comes here, whenever I sample, comes only from this zone. And then I will put another well which is away from this here, so that the two things don't get interconnected. And when I put the sampling here, please note, I want to do sampling here. My screen or my perforated pipe is, this is the level of sampling, is here. And suppose I seal the hole here with bentonite or cement grout. I am again making the fundamental error. Why? The gravel pack is all over. I think I am picking up the sample from here, but that is not the case. The water is falling through the gravel into your screen. So you have to either seal off your sealing should be here, so that no water can come from the upper layers and meet the bottom layer. So therefore, establishing the groundwater contaminant concentration requires picking up of samples from specific points, and you should not have any interconnectivity with the other points. Now, that is not what we do on normal wells and normal tube wells, and nobody seems to understand that. So you will go to any landfill site and you will find, do you have a borehole for monitoring groundwater? Yes, sir. So there will be one borehole. Where is the water table? 15 meters deep. How deep is this? Sir, this is 25 meters deep. But what are they sampling? Are they sampling from 15 meters or are they sampling from 25 meters or 20 meters? It's all mixed. Okay? You can have even a deeper well. So therefore, if you want to monitor at different depths, then you have to have either a well cluster or a multi-port device. A multi-port device, I will show you next. What will the multi-port device do? In a multi-port device, you will have openings at specific depths, and you will seal off the portions between those depths. Suppose I want to pick up 5 samples in one borehole, what will you do? And if I want to pick up 5 samples from the one well, I will make my hole, I will put a pipe with my screen or a port here, 1, 2, 3, 4. Then I must ensure that water does not cross from one port to the other. That means I will put gravel pack here, and then I will seal this. Then I will put gravel pack here, and then I will seal this. So that when I come to this hole and take the water, water only comes from here. The top water cannot fall into this. This is the zone of your sampling. So a multi-port device has got multiple levels of sealants in the annular space between the pipe and between the borehole. That is critical to, then again you put gravel here, and then you put your bentonite seal. Do you know how they seal the annular space? How do you seal an annular space between the pipe and the soil outside? You have made an 8-inch hole, you put a 6-inch pipe inside it, you put the gravel pack all around it. How do you put the gravel? You just put the gravel from the top, it goes into the bentonite slurry which is there. How do you seal it then? Conceptually, you can send a cement slurry and seal it, but normally you get bentonite pellets, like tablets. If you take any small bentonite tablet, it is nothing but bentonite powder which is compacted in the form of a tablet, and if you put it in the water, it will fall down like gravel. But once it falls down on the gravel below, it hydrates with time. As it hydrates with time, first the tablet will expand, then it's friable, so the whole mass will become one hydrated bentonite gel, right? And that is a perfect seal. No water can go through it. So basically, to seal the hole, especially for our applications like ours. You see, please understand, in a normal well, you are not trying to stop water from coming in from every level. You want water for drinking purposes or irrigation purposes. You want all the water to fall. Is that right? Here we are trying to say we want a water from a specific place. Therefore, this sealing becomes so much more important. So a multi-port device has multiple seals and water comes from, so then you will say, sir, but still in this it can get mixed. So your sampler goes and docks itself on this. Shall I say it again? A sampler goes and docks itself to the hole. Then you pick up the water which comes in the sampler, take it out, throw it away. Purge it 3 to 5 times. Then finally dock it and take the sample. Then if the sampler comes and docks itself, if this is the pipe and this is the port and a sampling device is coming down and docking itself means it attaches itself and you can open the dock, then you are only picking up water from that zone which is coming in from here. Okay? That's what a multi-port device is. So either you use well clusters or you use multi-port. Multi-port devices require a highly skilled operation to install them. You can easily go wrong, but your drilling costs are down. Here you have to drill 5 holes, here you have to put 1 device. Any questions on this whole concept of groundwater sampling? So a multi-port device looks like this. There is a particular type of sampler. We will not go into details of this. This can be a vacuum sampler or a pneumatic sampler, which goes down and stops at a particular location, attaches itself to it mechanically or magnetically, and it will get the water sample. Just to understand, first I am making the borehole. When I am making the borehole, I am using bentonite slurry. So all this black is the bentonite slurry or whatever slurry that you are using. Okay? Then I am putting in this pipe with these ports. Can you see this? 1, 2, 3, 4, 5, 6 ports, right? And then I have to seal. Can you see these black seals? 1, 2, 3, 4, 5, 6. This means these holes are only going to get water from here, from this white portion. Okay? I install my device, then I do the purging, well development. I keep all the ports open. And suck out the water. What is the idea of doing this? All the bentonite slurry or drill fluid which we have put into the soil, first that will come out. Well development takes weeks. It doesn't get developed in a day. So you allow the water to come out, you are disturbing the groundwater. So after the purging has taken place through the ports, you close all the ports. Then only that port will open where you want to sample and when you want to sample, right? And then with this sample, when you pick up a sample say from here or from here, you can tell me, sir, that this is the concentration of chlorides in this sample and this is the concentration of chlorides in this sample. Otherwise, you are giving me an average concentration of the chlorides, which will sometime be high. जब नीचे high वाले zone से ज़्यादा पानी आ जाएगा तो high हो जाएगा और जब दूसरे से आएगा तो low हो जाएगा. So this is the typical multi-port monitoring well. We don't use multi-port monitoring wells so far in India. We basically are still using single wells, but we can use a cluster of wells for which we have the expertise. In the end, I mean, after all the discussions that we have done, if I am only looking at subsurface contamination, please understand I can in the VADO zone put a lot of sampling devices. A VADO zone liquid sampler, vacuum lysimeter, soil gas probe, all kinds of things, downhole sensors. And in the saturated zone, I can use multi-port groundwater sampling or well clusters of different lengths. So, this looks very nice, but I can still miss a leakage which goes from here. So, which brings us back to the basic concept that I want to monitor everywhere. How do I monitor everywhere beneath a landfill? By putting a leakage detection system. So, all this is rarely done. All that we do is put a double liner. When I put a double liner, that means I am monitoring this entire yellow area. If something leaks, it will come into this and it will reach the site. I will not be able to tell you from where it is leaking, but I will tell you that leakage is taking place. So, I can identify the quantity of leakage, and then I can also have the alarm because the EPA has given us some values that if it exceeds, then we know we have a problem. But in continuous, if suppose I was to not have the double liner, but I was to have 100 samplers here installed, then I could tell you, okay, it came in this sampler, discretized sampler. But what happens is, let's go back to our landfill. The landfill has several phases in plan. Suppose you are doing 16 phases. Each phase will have a well, a sump and a pump to take out the leachate. So, we will be able to tell you that, look, this leakage is coming from this phase, but we will not be able to tell you what is the x and y coordinate of the point which is leaking. So, still double liner system is the best way to monitor everywhere underneath the ground. Okay? So, in comparison to discrete point monitoring, the double liner system with the leakage detection layer allows continuous monitoring everywhere beneath the liner system. Remember, if you have a municipality which says, oh, you have got a very big municipal solid waste landfill, please monitor. Then you tell him, please allow a double liner system. The cost is much higher, because if you are going to just put a few discrete point monitors in plan, you may just miss the leakage which is taking place. The double liner cannot pinpoint the point of leakage, but it can definitely identify the problematic phase of the landfill, because there will be different sumps to which all these leakages will go. So, this by and large puts us in the correct perspective for new landfills. I have a new landfill, I will still have the wells because I don't want anything to go beyond the perimeter. I'll have a double liner system if it's a hazardous waste, but I'll do a single liner system if it's a municipal solid waste, because that's what the law requires. Here in the new landfill, it is simple for me to decide where to put my monitors. But what about the old dumps? In India has got several hundred old waste dumps all across the country. When I have to monitor across an old dump, then the first question is where to monitor, and that is only possible to answer if I find the nature and extent of contamination. So, here the problem becomes totally different. In the case of a new landfill, the source is known. In the case of an old landfill, the problem becomes different in the sense that we know where the dump is. We know where the dump is. It's not that we don't know where the source is. So, if I look at it in plan, let's say that's my old waste dump. In section, let me see, that's my old waste dump. So, this is the section of my old waste dump, this is the plan view of my old waste dump. I also know from my site investigations that groundwater flows like that. Okay. So, I do know where the source is, but I don't know where to put my wells, because if the contamination has traveled, there's no point putting the monitoring well inside where the contamination has traveled. All that it will tell you is it is contaminated. After that, it will serve no purpose. If you put it outside the boundary, then you can tell whether the contamination has reached or not reached. So unless I know what the groundwater contamination plume already is, if it is there, then I can decide that okay, one upstream well cluster here and 3 here. And then I can say that I'll take some steps and ensure that it doesn't go beyond. But to do this location, I mean, in contrast, if I had put these here, it would serve no purpose. But to decide this, I've got to discover the boundary of the extent of contamination. That becomes an exercise in detection. Now you actually need a well which can move around, Idhar bhi check kar lete hain. Let us check here. Isn't that right? If you have to find the extent of contamination in a lake, let us say we find some contamination has started taking place in a lake. So you know that some pipeline is bringing in a contaminant. A lake is, let us say, 5 kilometers by 5 kilometers. You know the source, but you now want to know how far the contamination has traveled into the lake. So you will take a sampler and go plunging the sampler everywhere and taking out samples and say, sir, isme contamination. We'll start from the farthest point, no contamination, and come closer along some grid pattern. So the detection exercise is actually different. So in the detection exercise, you have to do some studies in a grid-like manner. What will you do? If say this is a few hundred meters, I'll first say let me go and check the 4 corners, right? And then I'll make a little grid. And if I detect something which says this has gone beyond, then I'll make a coarser grid. Agreed? And if I want to fine tune it, first I'll do the boundary. I know that it is not reached here. I know I'm getting a reading here, so then I'll do the finer grid. I might do the finer grid so that I can. And then on the basis of this finer grid, I should be able to give you how the contaminant varies in plan. Still, I will not be able to give you how it varies in depth. So if I have to give you how it varies in depth, and let us say this is the groundwater table, then what am I trying to say? I am trying to say how does the plume, how deep is the plume? So then again the issue comes that one point here means what? It means that you will sample so that you can tell me that look, my contamination is like this and it is like this in it's not here, it's not here, it's here. So basically detection is a different exercise than monitoring. Monitoring, the source is known, the original groundwater is pristine, or whatever is the local background levels, and we are just monitoring. Around old landfills, you'll first have to detect the extent of contamination. And we are still looking at subsurface contamination. So to detect, you should be able to do a lot of things in plan. First along a coarse grid, and then along a finer grid, and then you should be able to do something in section. At all these locations, you should be able to pick up discrete samples from different depths. Think so? If there's any other way of doing it, fine. So, we need to find the nature and extent of the contamination. Then we have to monitor at the boundary of the contaminant plume so that it doesn't extend beyond what it has gone. And then we have to take steps to bring the plume back or to do remediation and to improve the quality of the contaminated zone. So typically we will do reconnaissance and data collection. If there are some tube wells which are already there, or if there are some hand pumps in that area, you will go and pick up samples from all those areas because they're a natural source of information for you. You don't have to drill holes. Then you will conduct site investigations. And after you have conducted the site investigation, you will do monitoring. That means set up your monitoring regime, and then you will do a remediation design. How are you going to remediate? What has to be removed? What is the kind of treatment system you want? Are you going to pump out the water? Are you going to inject good water? Are you going to do in situ bioremediation? And then you have to take remediation action. So, normally it takes the shape from your leachate of the old dump. Please find out the contaminants of concern. Analyze the leachate and tell us which are the contaminants which are above the prescribed limits or in the background of the, compare the contaminants or the constituents of the leachate with the constituents of the groundwater which is on the upstream side. Those which will cause the groundwater to have elevated levels, those constituents are of interest to you. Amongst those constituents, the reactive ones are not of interest to you. Why? Because the soil will attenuate them. The non-reactive will go through. So, you will really be looking at your contaminant of concern which is non-reactive because it will lead the plume, right? And therefore, you can detect it. So, contaminant of concern, do some geophysical surveys, then you have to do sampling or drilling and sampling, both in plan and depth, coarse grid stage 1, fine grid stage 2. You can have strategy for the vadose zone and strategy for the saturated zone. Normally you attack the saturated zone first. If it is not contaminated, then you are very happy that the contaminants are still in the vadose zone, they have not reached below. Then of course, you have to, there are very stringent manuals on health and safety issues, especially if you are monitoring around a hazardous waste dump. Now, the advantage of geophysics or geophysical or indirect equipment is that it can be done very fast. So, you may do some geophysical investigations. For example, you would just do a electrical resistivity or an electromagnetic inductance survey right on the ground surface. You will have devices which can be rolled on the ground surface. You can have devices where electrodes can be put, but a reading can be taken in 10 minutes and then they can be put forward and then they can be put forward. Or you also have these electromagnetic devices which you can carry in your hand. You have a meter in front and you can move up and down. All that you are doing is looking for anomalies. Does the reading change? If it does, we will find out why it changes later. It may have nothing to do with the contamination. There may be a buried pipeline, there may be a water buried underground storage tank. Let's not get into that. Let's look at anomalies. So, we look at data about resistivity, conductivity, nuclear logs, capacitance, whatever we can get through geophysical methods. There is a greater volume of data. They are indirect, but they are continuous and they are anomaly detectors. So, if you have an anomaly, you have everything is going like this, but in an area something is going up or down, that means you have an issue. And in depth, if there are some tube wells already existing, please send down the borehole probes. These are also multi-parameter probes. You can measure electrical conductivity of the water, you can measure dissolved oxygen, you can measure pH. If you get anomalies, you have an idea that at some depths some anomalies are taking place. But do understand, one is above the ground sensors, geophysical methods, and the other is down the hole sensors. Down the hole will require you to either make a borehole and look at it or go down existing wells. The sensors are different. The next option is to try and do whole sampling. This is purely like our site investigation. We do undisturbed sampling. The undisturbed sampling is a whole sampling method. But the only problem is, in undisturbed sampling, we have to make a borehole. To make a borehole, we have to use a drilling mud to stabilize the hole. That is not allowed. So, typically, dry methods are preferred. Do site investigations along coarse grids for whole samples using dry methods. Hollow stem augering. In soil mechanics, we do SPT values what? Once every 1.5 meter depth, every 5 feet interval. Here you may instead go for continuous sampling. That means keep on just taking out samples. You don't have to measure N values. You take out a sample and you take out another sample, drill forward, take another sample. So you can do continuous sampling, pushing and sampling. Mostly you use stainless steel samplers. End caps and sealing is important. And once you bring these samples into the laboratory, you will extract the sample. You will isolate the faces. You will take out the gaseous phase. The whole sample which will come from the vadose zone may not have too much liquid in it. You will suck out the vapor or whatever is the gas. You will do the analysis of the gaseous phase and the liquid phase and the solid phase separately. You will send them to a chemist or a chemistry person to do the analyses. But your job is to give them the whole sample and to make the phases come apart. So you do isolation of phases, removal of bulk substances which are not important. You are not going to analyze the quartz of the sand. You are only interested in analyzing the material which is sitting on the quartz. So separate into separate chemical groups and do detection. All that you got to know is a whole sample is a good way of doing detection. But really what everybody wants to do is to be able to go down into the earth, pick up a sample, go deeper, pick up a sample without drilling a borehole, right? And one of the ways to do that is to use a cone penetrometer. So I'll come back to this, but this is our traditional electrical cone penetration device where a cone can be pushed down hydraulically into the soil. So two things happen. I'm using an electrical cone. Electrical cone can have a friction sleeve, a cone tip resistance, and it can also measure the pore water pressure. So the first idea is, as the cone is pushed in, you measure the friction ratio and the pore pressure ratio in the soil. Because we are looking at high permeability zones. High permeability zones will have water will travel faster, the contaminant can travel faster. So the electrical cone penetrometer, if you do the pore pressure ratio and the friction ratio, you will get plots like this. Wherever the pore pressure ratio is low or the friction ratio is low, indicates to you a high permeability zone. And from this high permeability zone, you will pick up a sample. And how is the sampling done? This is your traditional cone, electrical cone. This is a cone with a sampler. This outer sleeve becomes a piston sampler. When you go in, the cone is here, the sampler is around. When you have reached the depth of sampling, you can retract your piston and push this sampler into the soil and get the sample in this space. So the cone penetrometer, which is normally without a sampler, has to be now used with a sampler and becomes a more expensive equipment. So first do the cone penetration tests to identify the high permeability zones, then go to the high permeability zones and pick up the samples. Even better, let me show you the next. This is called filter tip vacuum sampling. It's a beautiful device. All of you have seen, you've seen a syringe with a needle. Everybody's had an injection put in their life, I hope. Or is this the new world where, like, in Mr. Spock, they come and put a gun and they give it a blast and everything goes in without a syringe. Well, when they use a syringe, in that injection bottle of the old type, there used to be a rubber top, and you could put the needle through this rubber top, apply suction, and the material would come due to vacuum. And then you take out the syringe, that rubber top seals itself again. It's so designed that nothing comes out of it again. That part of the injection can be even used again. And that top of the bottle is called a septum, a rubber septum. So in this device which I am showing you here, this device is used with a static cone penetrometer which has a filter tip. That is the piezo cone. That's the cone, that's the filter. So here is think of a test tube, right? Think of a test tube with a rubber septum at the top, like that at the top of an injection bottle. And it is evacuated. That means it has a vacuum inside it. This is the basic sampler. What do? There is a septum here and there is a septum here. When the cone is being pushed, this needle is not there and this sample vial is not there, it is outside. And the rod is hollow. You push the cone and take your readings of the cone penetration, resistance and the friction ratio, skin friction and the pore pressures. When you reach the high permeability zone, what do? You send in a needle, the same needle as you have in an injection, but it is pointing to both sides. This needle is lowered and it comes and touches this septum. Okay? On top of it, you send your test tube with the septum. Now what is it? This needle is touching this septum and this part of the needle is touching this septum. Okay? Then on top of that sample vial, you put some weight or a pressure transducer and you make the needle under the weight go into the, first it will go into the lower septum in here and then it will puncture the upper septum. This vacuum will get transferred to this filter tip. And what will come in? Whatever water is here will get sucked into this vial. And here is the water coming in. And when you are finished, just pick up the thing. The lower septum will get sealed and the upper vacuum vial will be full of water and it will also become sealed. Suppose you are sampling in the Vadose zone, what will come in? Air. Or suppose you are looking for petroleum vapors. If your underground tank has leaked, then petroleum volatile organic vapors will be there in the void space. With the filter tip, you can get pore water samples or pore gas samples. And when the vial comes out to you, it's all sealed. No human being has touched it. No end cap sealing is required with wax or with a stainless steel cap. It is self-sealed. So for fluids, the filter tip vacuum sampling is the ultimate in cutting edge technology for the purpose of sampling fluids, whether gases or whether liquids. But you have to use it in conjunction with a electrical cone penetrometer. And do you remember how much electrical cone penetrometer costs? I had discussed this with you in the class on site investigation. Some idea? 20 lakhs. I think it's more, multiply that by 5 times. A full-fledged, I just showed you the electrical cone penetrometer here is truck mounted. You're going to put these samples in this laboratory which will have constant temperature at 22 or 25, whatever is the prescribed temperature. This truck itself will cost how much? So whatever. So the whole device will cost you about 100 lakhs or more. But the quality of samples that you will get, from each depth you can get a sample and you can analyze it and give. So such are the devices which are used for taking samples from different depths. If you want the whole sample, then you have to have the cone penetrometer with the sampler, the piston sampler which I showed you. But if you just want the fluid samplers, so this is for the whole sample. The whole sample will come in this. But if you want the fluid samplers, you will use this. Okay? So the cone penetration device can typically work up to 20-25 meters depth, 30 meter depth. It can't work up to 100 meters depth. Why? Very difficult to push the cone in. Then you have to go back to your boreholes. But also there is one more device which is a much smaller device. Suppose your water table is say in the top 5 to 10 meters. This is not a sophisticated device. This is just a 1-inch diameter drill rod which is hollow from inside and it is inserted into the ground with a percussion hammer. What is the percussion hammer? The same hammer which you see by which you also do demolition. It goes up and down, up and down, up and down, up and down. It's pneumatically actuated. So this percussion hammer is able to send this rod down into the ground by few meters, 5 to 7 meters. If you look inside this rod, what is happening? I just want you to see this. 5 to 7 meter, the sample can be picked up by applying suction. Beyond 10 meters, you can't pick up by applying suction. You have to send in the sampler to retrieve. So what happens is, this has a conical tip. When you reach the depth that you want, this tip can either be discarded, or it can open a port and you can suck out the water, and through this tubing the water will come into a sampler at the top. So these are small diameter probes. At a site, they can do sampling for you at every 1 meter of the liquid only. But the advantage is they can go down very fast. You are not bothered here about whether you are destroying the structure of the soil, whether the strength has changed, whether you are getting undisturbed sample. No. What are you bothered about? You would be able to reach a particular depth and pick up the liquid sample or the gaseous sample by suction. So for small depths, we have special probes which can be pushed or driven into the ground to collect the samples by suction. So both these devices which I have talked about, the small dia probes, so this whole thing is actually mounted behind a van. When you are traveling, it just folds into the van, and both these devices, either the small probe or this, they are used for detecting the extent of contamination. They are not being used to monitor a fixed source. To monitor a fixed source, you need a device which is there embedded inside all the time, which is a well, a multi-port well or a well cluster. But if you want to find out how much contamination has already occurred, you need a device which is mobile, which can go into the ground, pick up the samples for you so that you can analyze them in the laboratory, and you can then tell the extent of contamination. And these devices are used in conjunction with the geophysical results. If the geophysics shows you that there are anomalies here and there are anomalies here, then you will target these locations for getting the sample to prove whether the anomaly is due to contamination or whether the anomaly is due to something else which is underground which we don't know about. So in this manner, in all landfill sites, first we detect the extent of contamination and then we monitor them just the same way as we are monitoring new landfill sites. So with this, I have covered for you the entire spectrum of environmental monitoring below the ground. The vacuum filter tip sampler is by far the most sophisticated technique in which you can get the liquid and the gases, and you can do the analysis in the laboratory. The multi-port groundwater well is the cutting edge for taking samples in one borehole from different depths, for whether you monitor it once a month. You see, the groundwater doesn't travel very fast, I have already told you. So you may monitor groundwater only once a month, but at least you are able to pick up the samples from the different depths, and you know there is no contamination at the top, but no, you are getting a slight increase in reading at mid depth and there is no contamination at the bottom. And with these devices, you can monitor your old and new landfills. It's tough, it's expensive. It's very easy to miss contamination. Please understand. I can go to a site and say, oh, I did 2 boreholes, there was no contamination. Hence, hereby it is certified that the landfill is not leaking. What you have to actually do is to hunt and sniff around for the contamination. And after you have done enough, then say there is no leakage or it is not causing underground contamination. Any questions which come to your mind? No questions. Wonderful. But I do wish that you read up upon how we are, how a normal well is so different from a monitoring well or a monitoring well cluster, and how screen length is not important in a normal well, where the sealing is done is not important in a normal well, and how it is so important in a groundwater monitoring program, quality monitoring program. Okay, we'll stop here. Have a good day.